Now we will see how changes the diagram of the shock absorber when we modify the diameter and section of the bypass. Suppose that in the original shock absorber that we saw previously, we had the blue diagram. And suppose that we obtain the blue diagram using only one bypass made with one single hole with a diameter of 1 millimeter. If the diameter of the hole is 1 millimeter, the section of the hole will be 0.785 square millimeters. Now suppose that we increase the diameter of the hole and it achieves the value of 1.42 millimeters. In this way, the section of the new bypass will be 1.570 square millimeters. It means that if the new diameter is 1.4 times the original diameter, the new section will be the double of the original diameter. So the new bypass will be the double of the original one. It means that if the flow is the same, having the double of area, the speed of the oil will be the middle. So we will have the same resistance but at the double of speed. So suppose that we have this value at 0.065 meters per second. Now the same value of force will be achieved at 0.13 meters per second. Suppose that the 70 kilos were achieved at 0.13 meters per second, now will be achieved at 0.26, and so on. So the new diagram will be the red one. So you see that if we duplicate the area of the bypass, the new diagram will be dramatically softer. And why? Because we hadn't lines, we have parabolas. So in this case, look, at the same speed, we move from 70 kilos to 18 kilos. It means that at low speeds, we have a shock absorber that is 3-4 times softer than original. At medium speeds, the ratio changes and decreases. And then going to high speeds, the difference gets smaller and smaller. So what is important to understand? That if we change the section of the bypass because we increase the diameter of the bypass or because we increase the number of bypasses, the behavior of the shock absorber change a lot, but change mainly at low speeds, because at low speeds all the resistance of the shock absorber depends only from the bypass, while at high speeds, after the G point, depends from the bypass, but especially depends from the spring. Now suppose that instead of increasing the bypass, we decrease the bypass. So, starting from the blue original diagram, we make a hole that is 0.23 millimeters of diameter. The area will be 0.39 square millimeters, 50% in comparison with the original one. It means that we will have the same forces with the 50% of speed, and the result will be the red line. As you can see in the red line, the laminar flow almost disappears, and we start practically with the turbulent, and then in G the valve opens and gets laminar again. In this case, we will have a shock absorber that in comparison with the original, it will be harder and harder. Just to make an example, suppose that this was original. We can imagine that this is the version for people that need a lot of comfort because they are driving with old people. Okay, so we need a very, very soft shock absorber. This could be a standard shock absorber, while in this case we have the shock absorber that has been modified in order to make tuning. Okay? Now suppose that we remove the bypass. We erase the bypass. In this case, we will have a sort of preload of the shock absorber, because if we don't overcome the value of the resistance of the spring, it will be impossible to extend or to compress the shock absorber. This solution is used only in few special applications. For instance, on those cases where you want to lose the grip of the tire. Just to make an example, could be on the rear axle of Renault Clio First Series or Peugeot 106 First Series. In this case, the big problem of the car is that it is too much understeering at the beginning of the cornering. In order to reduce the understeering, we can block the suspension, and we block the suspension blocking the shock absorber. And we block the shock absorber removing any kind of bypass. In this way, we will have a very hard shock absorber in compression and preload. It will be possible, and rebound, it will be possible to increase a lot the preload of the springs without pumping. In this way, the sway bar will be very effective, the car will not roll, and we will reduce a lot the understeering of the car. But of course, this is a very special application that you cannot use on automotive applications, because the car would be too much reactive and too much dangerous. And of course, you cannot use on a motorbike. Now, suppose that we keep the bypass as it was, okay? Which don't change any bypass. We just change the preload of our spring. Let me return at the beginning. Here we have the spring. Suppose that we don't touch the bypass, we increase the preload of this spring. If we increase the preload of this spring, nothing changed here. But of course, we move the G point towards. And in this case, the turbulent flow resists more and more. We make this if we want to reduce, for instance, the pumping of the car. So we want a car that is harder than originally, but only from medium speed in advance. And this could be useful in order to not modify the pitching and rolling, but to modify the pumping. Another situation could be if we keep the original preload, but we change the spring and we put a harder spring, but with the same preload. Because the same bypass, nothing changed from 0 to G. Since the same preload, G is not moving up or down. But because the new spring is harder than originally, the new diagram will be harder after G. This could be used in order to reduce the pumping or other type of behavior of the car but only at higher, very high speeds. Now, the last example. Here there is the speed 0, 0.13, 26, 39, 0.52 millimeters per second. So now we speak about very high speeds. If we have the valve with the holes E and C with big diameter, we will have laminar flow even at high speeds. Or we will start to have turbulence only at very high speeds. Suppose that we make pistons with smaller holes. We will have to have turbulence in advance, and the shock absorber will get harder at lower speeds. Of course, in an automotive application, where the first aim on the setting up is the comfort and safety, we look for pistons with big holes in order to have laminar flow at very high speed, because in case of shocks of the suspension, the car will remain comfortable. Of course, on races, depending on the application, we can need one shock absorber much more harder at high speeds. And in this case, the technician chooses a piston with smaller holes. Thank you.